Okay, so the last application from section 3.7 that we're going to look at concerns economics and business. So this is an application that you would be working with a whole lot if you took a Calculus 4 business class, which we offer one of those at Sac City. So let's get into it. In this application, let's suppose that the total cost that a company incurs by producing X units of some commodity is given by what's called a cost function, C of X. So, we're assuming that this is a company that produces some kind of product, and the number of units, however you measure that, is represented by X. The cost of producing that number of units is equal to C of X. It's a function of X. Then let's suppose that the number of units produced increases from one value to another, so x1 to x2. Then, similar to what we did in the last video with population growth, the corresponding change in this function, the change in cost, will be given by delta C, C of x2 minus C of x1. That's how much the cost increased by. Okay, so this naturally leads to an average rate of change, and that rate of change would represent the rate of change in cost with respect to the number of units produced over that interval, x1, x2. And it's given by this, delta C over delta X equals C of x2 minus C of x1 over x2 minus x1. Very similar to the rate that we looked at in the last example. But this time we're going to also represent the rate in an alternative way that we already encountered back in the end of chapter 2. We defined the derivative. I can alternatively set x2 equal to x1 plus delta x, right? Because that's how much the number of units increased by as we moved from x1 to x2. So that would become x1 plus delta x right here, and then down here this would just represent the change in x delta x. Okay, if I take the limit of this difference quotient as delta x goes to 0, then once again we have a derivative, and this time it would represent the instantaneous rate of change in cost with respect to the number of units produced. And this function goes by a very specific name. We call it a marginal cost function. We talk about these a whole lot in business calculus. The marginal cost function is the derivative of your cost function. Okay. Now, once again, in the case of this function here, we have an issue of it being the domain of this function being non-negative integers. We can only plug in whole numbers for this function, and the reason for that is because the number of units that we produce, it only makes sense to measure that using whole numbers. We're going to assume that anyways. So once again, you would have to do some kind of approximation to this function with a continuous or a differentiable function in order to be able to do this kind of a thing with it. So we're going to basically ignore the fact that this function would normally not be differentiable because we can approximate it closely enough with a function that is differentiable. With that in mind, before we talk about before we get into an example, I want to talk about what this marginal cost function tells us, how we can interpret it. So if the total cost of producing X units is relatively large, which would mean if X is pretty large, if we're producing a lot of units of whatever this product is, then setting delta X equals 1 would be a relatively small number relative to X, okay? So basically all that means is that we can approximate this limit here by setting delta X equal to 1, because it's relatively small, relatively close to 0 compared to what we're assuming our cost is going to be. Then what that does is if I try to evaluate C prime of n, but not using the derivative explicitly, using this approximation where I'm setting delta x equal to 1. Then x1 becomes n, delta x becomes 1, and this becomes c of n plus 1 minus c of n over n plus 1 minus n. That's what delta x would look like. That's just equal to 1 down here. And I get c of n plus 1 minus c of n. What does that mean? Well, again, this means, if you look at the approximation here, it means the derivative, the marginal cost function, evaluated at some value n. We oftentimes call this the production level, the number of units that we're producing. is approximately equal to C of n plus 1 minus C of n, the cost of producing n plus 1 units minus the cost of producing n units. What this is equal to, after you subtract, it's the cost of producing one additional unit after you've produced n units. That's what this difference represents. And the marginal cost function approximates that value. Okay? Now, we're going to use that in an example on the next page. Cost functions, C of x, are usually given as a low degree polynomial, usually a second or third degree polynomial. Okay? And if we look at this polynomial, it's helpful to kind of think of where these terms might come into play for an actual cost function. First of all, you have this constant term here, a. A is the only term in this polynomial that does not depend on x. So regardless of how many units we're producing, this constant is always present. In business math, we would call that overhead. It's also called fixed cost. So basically, it's whatever costs you accrue that are independent of your production. This can be things like rent for your facilities. Whether you produce 1 unit or 1,000,000 units, you still have to pay the same amount of rent for your facilities. It can be other things like temperature control, the cost of utilities and maintenance and things like that. Those are all fixed costs. We call that overhead. Other costs will depend on how many units you produce. So for example, whatever the product you're making is, it's going to require a certain number of raw materials. And we would expect the cost of those raw materials to have a direct or a proportional relationship with the number of units produced. So this term right here, this linear term, b times x, is generally going to represent the cost of those raw materials. Other terms where you're squaring or cubing your x, something like this, those terms also depend on the number of units produced, because that's what x is, but in a non-linear way. And your book kind of explains this a little bit. You don't need to know exactly where all of those factors come into play, but things like labor costs are one place that these terms are accounting for your cost. Labor, because if you're producing a large number of units, that requires a more complicated operation. You have to hire more people for that. Their jobs get much more specific, and that kind of convolutes it a little bit. You may also run into overtime, which increases the amount that you're paying your employees and stuff like that. It's more complicated than just a linear relationship. So now that we've talked about that, let's do an example where we want to look at a marginal cost function. And interpret it the way that we did on the previous page. So it says the cost function for a given commodity is given by C of x equals this cubic polynomial, 84 plus 0.16x minus 0.0006x squared plus 0.000003x cubed. Okay, the cost is going to be represented in dollars and cents here. Find C prime of 100 and compare this to the actual cost of producing the 101st item. So two things it's asking us to do here. C prime of 100 is first. I'm going to find C prime of x and then just plug a 100 into it. So constant term is going to go away. I'm going to get 0.16. Power rule here, 2 times this would give me minus 0.0012x plus power rule here is going to give me there was 5 zeros, 9x squared. Okay, so now I need to plug 100 into this. What would C prime of 100 be? If you know how to work with powers of 10, you don't need a calculator for this. Okay, so this is equal to 0.16. What happens when I multiply a decimal by 100? It just moves the decimal point 2 spots to the right. That means this is 0.12x. Now this is not 100. I plug 100 into x, but then I square it, which gives me 10,000. If you multiply a decimal number by 10,000, that moves the decimal point 4 spots to the right, leaving me with plus 0.09. I don't know why I shouldn't have included the x there because I would have plugged 100 in for that. So this is 0.16 minus 0.12 plus 0.09, which is equal to 0.13. Now remember, this is cost. This is marginal cost, which is a rate of change, but we can interpret it as approximately equal to the cost of producing one additional item after the 100th. So it would be the 101st item. Okay, so that means I can think of this as 13 cents. That would be approximately the cost of producing the 101st item. I've already produced 100. To get that 101st item off of my production line is going to cost me, the company owner, an additional 13 cents. How do I verify that this is a good approximation, though? Well, I would need to find what the cost of producing the actual 101st item is using my cost function. And that, it's not just C of 101, okay? Because C of 101 is equal to the cost of producing a total of 101 items. Not the 101st, but all 101 of those items. I need to subtract the cost of producing the first 100 items to get the cost of that final 101st. This is just a matter of plugging 101 into the original cost function, 100 into the original cost function, and subtracting those two. That's a bunch of arithmetic that's not worth our time to write all that out. Use a calculator for that. This comes out to 0.130303. And again, this would be measured in dollars. Okay, so this, we can't have, fractions of a penny in practice, but the quantities like this would come into play when we're talking about large numbers of items that are being produced. Notice that this would in fact round to 13 cents. This is a very, very good approximation for the true cost of that 101st item. So we're seeing that interpretation of the marginal cost function works, at least in this example. Okay, that's where we're going to conclude 3.7.